Okay, so I will describe the project that is due on September 27th. That's a Sunday at 23:59. And it is about the theoretical analysis and empirical analysis of the Gale-Shapley algorithm and compare both. Well, first remember that the theoretical analysis has already been done, and you can see the results on the slides. The conclusion is that this algorithm runs in a quadratic time. So if the function defining the way in which the number of steps required to solve a problem increases as we increase the size of the problem is similar to a parabola because it's quadratic in nature. Then, so this project is asking you to implement the Gale-Shapley algorithm in two ways. One is a demo implementation and the other is a scriptable implementation. Let's see, what do I mean by a demo implementation? So this is, by the way, what you are looking at is a directory where all the files relevant to the project are contained. There might be lots of them, and you might include here not only code, but README files, auxiliary files, data files, and even screenshots. That's what I want to see in your directories. Now, I was telling you, what do I mean by the demo version? I assume that everybody is already done with that project, and what I mean is a version of the program that takes an input, okay, like an arbitrary input, which is hard-coded by ourselves. In this case, for example, we have 10 people. Amy, Zeus, Victor, Wyatt, Jancy, and Xavier are the boys, and Bertha, Claire, Diane, Erica are the girls, and we have the following preference arrays for them. So this program is supposed to output each of the decisions made by the algorithm. For example, we know that first someone has to propose to someone else, so Victor proposes to Bertha. We need to record the outcome of that decision, that proposition. Bertha has to decide, and we have to report whether she accepts or rejects and the reason why, and then who's proposing next, and so on. Of course, we may get some cases of rejection when like here, Wyatt proposes to Amy, but Amy rejects since she prefers Victor to Wyatt, and we can check that in Amy's list over here because Victor appears before Wyatt, as it should. So in that way, we can track and check the correctness of the algorithm, no matter what the input is. And in the end, we produce the list of the stable matching Victor, Amy, Wyatt with Claire, Xavier, and Bertha, Yancy and Erica, and Susan and Diane. That's the final result of the algorithm. Then we use, if we look at the algorithm, which is es.py, let's take a look at the code and look at the first, look at line 11. So here's where in this version, which is just the version for the demo for a toy-sized problem, for a demo that we are able to check, we are reading the input from a file. And that file is named gs_data_ch1. And that file is going to be interpreted as code and executed by this statement. And what is the consequence? Well, let's first take a look. So this is we want to see what is inside the file gs.data.ch1, and pretty much we have the definition using the Python syntax of the of a problem, which means which boys, which girls, and the preference lists for each of them. And we can change them. This has been arranged to reflect exactly the same people and same preference arrays that we saw or that are shown in the slides, so that we can check it furthermore. But we need to add more cases other than this one, and perhaps with other people. And we need to check whether it is correct or not. That's perhaps something that is shown here in this other output or sample output, where we have different participants and different arrays of preference lists. And then we have all the decisions reported, and finally the final pairing. And here we are given even the timing and asked if we had another trial or not. Okay, so that's this first part. That's the demo implementation. I think that by now everybody should have it very clear and had already done that, because it was due not so long ago. Now let's talk about the scriptable implementation. A scriptable implementation means something that can be run online, from online. Okay, so that means that we call the problem by just invoking its name online, and we get some results. An example of this, let's see, let's begin again. I have a problem in C, which has been compiled and called GS1, and it takes a command line argument, and that's what I wanted to do. I wanted to take, for example, to create a test set of size 1000, so 1000 boys and 1000 girls, and for each boy a preference list, and for each girl a preference list also. And those preference lists need to be randomly shuffled, so they need to be different each time. And so when I run this code, what I get is only two numbers, which are the size of the problem, which is 1000 in this case, 1000 boys, 1000 girls, and so on. And this is the time it took. Why do I want that scriptable? Because if I want to be able to run it many times, just from the command line or even with a script. This is, if I run it again, even with the same size, I am likely to get a different number for the time, because the problem, even these two problems, even if they are of the same size, they are not the same problem, and one might be easier to solve than the other one. And if I just run it again with the same size, I can get another different result. But that's what I want. Of course, if I run it with another number, another argument, let's say if I like 3000, so this would work a little slower, because it has to work with 3000 people. And if I run it again, so we're getting big numbers in the time. And that is what I mean by scriptable, because we should be able to run all our experiments from a script. So what's that script? That script is called run GS1. So let's see. So let's see. GS1. This script is a bash script, which can be, you can see that in the first line right out of the bat. Oh, let's see. So line number 1 is about, it tells the system that it's a bash script. And let's ignore all these comments. The significant code is in these 3 lines and the last one. And what are these 3 lines? Well, this is just a for loop, and it's going to, what is that for loop doing? Well, it is doing this statement. It is running my scriptable version of the program, which is GS1, with a different argument every time. This variable I is substituted by whatever value comes from the I loop control. And this for loop control starts in 1000, stops at 5000, and has increments of 1000 at a time. So that means that we will be running this program. We will be calling the program and running it with problem size 1000, 2000, 3000, 4000, and 5000, and then it will stop. And at each time it runs, it will append the output to a file that should be created, or if it's not created, it will create it, and it's called data.txt. And what we will take care of the last line later, but what is that good for? Well, we were talking about the script run GS1. Let's see what it contains, what's in it. And so this is it, and we already covered what is in it. What I wanted to show you is now the contents of the data file. So you know that the file data.txt is the file where we are appending the results of each new experiments. Wow, this is a file that we can see. In that file that we have run actually 5 experiments. Here's the first experiment, or the first series of experiments. Actually, this is the last one. Well, no, that's the first one. Then the second time I run it, I got these other times, and then the third time I run it, I got these other times, and then there was another time I ran it, and I got this other time, and finally this is the last run. These are the times I'm getting for this project. Okay, so then that's what I mean by scriptable. So scriptable implementation means something that can be called from a script. Of course, there are some requirements for that scriptable implementation. One of the requirements would be, even if it's not told in here, is that it is implied by this, or probably told with better detail on here, that you should implement the following changes on your code. So you first need to stop using names, but use integers to denote the suitors and the girls. And then, we talked already about having taking an argument from the command line. It should not be interactive. It should not be interactive, but run at execution time. And it should have a way to toggle detailed output. We'll go over it. But the point is that it will have to create its own test sets. So if it gets an argument of 2500, it should be able to create 2500 arrays of preferences for the boys, and 2500 arrays of preferences for the girls. And then the code that would be running is the same code that you use for the GS demo. So that's what I mean by that's something that your code needs to do. And it also needs to insert timing functions and accept command line arguments so it can do what it's supposed to do. Okay, and maybe you would like to know a little bit. I can give you some hints on how to do that. So let's say for the first part, to create the test sets, what we are going to use is the Fisher-Yates shuffle. Okay, and why is that? Because to do them, to implement them, the way, the strategy that really would work, is just create an array of 2500 by 2500. Well, supposing that that's the input you got. If you get an input of 1000, then you would create arrays of 1000 by 1000. And whatever size your array, n by n, where n is a big number, should be filled with each of those arrays, each of those rows of this array, each of the subarrays, or each row should be initialized to have the integers in increasing order from 0 to n minus 1, so that they can serve as the indexes. They can serve as indexes. Or in fact, if we use the standard initialization procedures, you can easily initialize the arrays and the array with the number 0 to 999 if n equals 1000. And now we need to shuffle them, and we don't like an ordered array of preferences because we need to resemble reality. So we are going to shuffle them at random. The way to do that, there's many ways to do that, but please do use the Fisher-Yates shuffle because it runs in linear time. It is very easy to code this shuffling badly. Okay, so what do I mean by shuffling? Well, let's say you start with an array with elements in which the elements are ordered in an increasing size. Only we are representing the numbers here as some function or proportional to the slant of the little lines that we see in this array. So when we shuffle them, one way to do that, a naive way, will be, okay, well, create an array, a destination array, and now you would have to pick them, pick all the elements consecutively and at random, and put them on the auxiliary array, and then so you need two arrays, and then it wouldn't be really very fast, because we would be getting a sparse array each time we take an element from the original array and put it on the auxiliary array. We have to do some compression so that we can select it from the smaller array, and all that takes a long time. There is an even worse way to do that, which is, for example, like in this code. Okay, we also have an auxiliary array, and we are going to pass the elements from the original array to the auxiliary array. They will be chosen at random, and then we will have to check if an element hasn't already been shuffled. We move it to the new array, but it has already been shuffled. We need to pick another element. So in the beginning, we would pick one element and at random and put it on the auxiliary array and check if we have already used that element before and shuffle that. And so here in red, you would have, in fact, I think this is not running as it should. So this is what happens. So you see, as we pick more and more elements and we occupy more and more positions, chances are that the checking gets complicated, because we might pick repeated elements and we need to check if they had already been shuffled or not. And that checking time increases a lot as the auxiliary file gets bigger and bigger. So this is definitely a no-no, and do not code anything like that. And sometimes you might be using an initialization procedure which you're copying from the internet and you're not sure who wrote it. It may be a poor performer like this one we're looking at. But bad performance can also appear in some other ways. For example, in here, where we have the when we are taking from the original array and copying to an auxiliary array, and but we now pick at random and make the original array smaller, and then we pick from the smaller array a random element, and that's what we continue doing for each of the positions of the consecutive positions of the auxiliary array until we're done. This is the way we would do that. And you would say, well, that's pretty efficient. Actually, it's not. It runs in big O of n squared, and it even if you see that it has only a single while loop, it is still n squared, because whenever we process the array, we need to scan and to compress the remaining array that could be full of spaces, or would have one more space because we have just taken one element out of it. And so we have to make it smaller, and we have to find the place that got empty, and that means we need to scan it. So we are actually doing a scan within a scan. That's n squared. But the winning idea is what is called Fisher-Yates, or Knuth, because Knuth was the first one to come or to report this idea. The idea is very old, but it essentially means that first we get rid of any auxiliary arrays. You do that in situ on the same array. You start at the end of the array, you pick the last element, and in some way signal it or separate it or reserve it. Maybe keep a pointer or keep a variable with its index. Then, so if you have, for example, the numbers 0 from 0 to 999, get the number 999, and then pick a random number between 0 and 998, and that will pick randomly any of the elements to the left of the last one. And then once you did that, you just switch the elements, the last element with the chosen element. Okay, and the switching is done, well, you get this to an auxiliary temporary memory location, then you get this to this chosen element to the final position, and then the one that you had in the temporary store gets put back in the place of the randomly chosen element. And then we have already successfully switched one position, the last one, and we go to the next to the last one. So this one will be interchanged with another element. So we pick a random number now from between 0 and 997, and whichever element we get will be switched with the next to the last element, and then we move one position to the left, and that element arrived to would be switched with an element chosen at random from the 996 elements on the left. And we do that over and over and over. Obviously we do not need any auxiliary arrays, and since the part of the array that hasn't been shuffled is getting smaller and smaller and smaller and smaller, it will run faster towards the end. And in fact, this is a linear time algorithm. This is the one that you should use. If you don't use this algorithm, it is coded in JavaScript, but you can translate it easily to any other language that you may be using. If you're not using this particular algorithm, you may have to wait for your runs a long time, and we don't want to do that, because in fact, if you give me such a program, I wouldn't even grade it, because I don't want to wait an hour to be able to grade someone, to see if someone's program works or not. So make sure whether you code it or not, whether you use, for example, it might be possible that that Python has a library which implements this kind of shuffling. Well, you just have to believe on that, but you would need to find all the evidence that it's a linear, that it has a linear running time. It's an algorithm that runs in linear time, a big O of n. So that's something you need. Then what is the difference? Let me run the script again. Before I run the script, because we would see the results. Let me comment again on the script, on that last line of code, which is this one. And when it starts, gnuplot dash minus persist model.gpt. Okay, so what is it for? Well, gnuplot is a utility that is very common in the Linux environment. If it's not already there in your Linux version, if you're working in Linux, then you can easily install it, find it and install it with app-get. And the minus persist option, this is an option that tells gnuplot, please, when you display the plot, then if you display a plot or whatever plots, please do not make them disappear, make them persist on time so I can see them, because if you do not include this parameter, your plot would just flash on the screen and then disappear immediately within a fraction of a second. So you don't want that. That's why we want to add dash persist. And then model.gpt is another parameter, which is the name of a file, which is passed to gnuplot, where we tell gnuplot what kind of a fit we want. Because in the end, what we want to do is we want to fit the data, okay, as we are saying here, conduct an empirical analysis of the algorithm and fit the theoretical model. And I would like to explain you what I mean by that. So what is that? Let's say, to do that, I will take you to Desmos. Let's do that with Desmos, which I love it. It's just a very simple app. And let's say that we have, look at the numbers within parentheses here in the left lower part of the screen. And let's assume that these are pairs of points that come from the experiment. An experiment such as the one we performed with our algorithm. We run an algorithm with a given size and we get back a given time. And then, so let's say, we run an algorithm of size 2, and then we got at a time of 3, whatever units we use. And this can be represented on a plane if we use the corresponding coordinate axis. In this case, the horizontal axis will represent the size of the problem, and the vertical axis will represent the time or the number of significant operations used by the algorithm to solve the problem it's supposed to solve. And then let's say, so that's 1 point. Each time we run an experiment, we get 1 point on the plane. Let's say we run it again, but this time with size 4, and we get reported back a time of 18.7, which would correspond to the green point or blue point on the screen. And then we perform another experiment with an input size of 6, and we get the point, the green point when we represent it, because we get a time of 32, and this would be the green point. Okay. Now we know that those points are not really arbitrary. If we did everything correctly, if the algorithm was coded appropriately with the right data structures, then it should run in quadratic time. And what does that mean? Well, take a look at the top of this left part of the screen, and you will see, well, we have this is a second degree polynomial. Y equals ax squared plus bx plus c, and that's a generic quadratic polynomial. Okay? And a, b, and c are supposed to be numbers, only we abstract them here to symbols so that we can write a general formula. So each time we plug in some values for those coefficients a, b, and c, we might get a different parabola or a different curve. Let's see what happens if we plug in 1.1 for A, 0.1 for B, and 1 for C. This means that look at the coefficient of A is big compared with the coefficient B. The coefficient B is is very small, and the constant term, which is the third coefficient, C, is 1. And it corresponds to this parabola you're seeing now. Okay, so this is one parabola. And what happens if I modify the different parameters? So let's modify C. Let's move C. If I make it bigger and bigger and bigger, then the parabola goes up and up and up. And if I make it smaller, smaller, and smaller, then it goes down. And so let's say we might get it back to 1. And then what happens with the second coefficient, with B? Well, when we move it around, it becomes more and more positive. We go to the left and down, moving the apex of the parabola, or to the other side. So it looks like we are moving the apex of the parabola on top of another parabola that is looking upwards rather than downwards. So this is the effect of the second coefficient. And we had a 1.1 or whatever we had. And then the first coefficient, if we make it bigger, the parabola gets steeper and steeper and steeper. And if we make it smaller, then it gets flatter and flatter, even to a straight line, and then we can even flip it if we make it negative enough. So in other words, this equation defines an infinite family of parabolas. But of all those infinite parabolas, I want only one that fits these points the best. Now, it may be impossible that a parabola may pass through these 3 points, because there might be some measuring error, because all experiments have measuring error. And in this case, the uncertainty comes from different sources. It may come from principally or mainly because we have different problems, and we have variation when we assign a random problem. Some of them are easier to solve than others, and so we may have different running times. So, but out of all those parabolas, I want the one that fits the data the best. Something like this. Let's say I want to probably get this a little bit, or get to the right or to the left or whatever. And we might have one point going exactly through one of the points. But of those parabolas, there's only one that minimizes, let's say, the square error, the vertical distance between each point and the parabola. And that's the one we want to choose. Okay, that's the so that's what I mean by fitting a curve. Now this is going to be done by gnuplot itself, and that's why gnuplot needs information about the model. Before I run it and run the script, then let's see what the contents of that model.gpt file that I was talking about. Oh, let's show it again, only with less clutter. So in this file we pass gnuplot the relevant information for making a fit. And as you can see, the most important part of the information, well, what model do you want to fit? I want to fit the parabola. That's why I'm writing the equation for a generic parabola. And this is just the same, basically the same equation that we saw. Only instead of A, we have A2, instead of B, we have A1, instead of C, we have A0. But, and for the initial parameter values, we have A0 is 1, A1, A2 is 1. Then we perform the fit, and the fit is using the data taken from the file data.txt, which is the data containing all the results of all the runs, and then we draw the plot, and a plot will be drawn, and we just tell gnuplot how to label the x and y axis, and that's what it would do. So if I run my run GS1 script, I have to wait some time until, so it doesn't take long. It runs it 5 more times. Now I have one more experiment, so I have more points in my plot. And you can see in this plot that we have some spread. For lower values of the size, lower values of n, or lower values of x, we have little spread. Almost all of them take the same time. But as the size increases, there is more variation in the time that the algorithm might take. And this is the, let's say, the parabola that would be the best fit. Now, this is the plot of the parabola that would give the best fit. If you want the details of the parabola, you can see them in the output, this output given by gnuplot. And so when we run gnuplot, here it is. When we run gnuplot, this is the fit, the final result of the fit. It's an iterative method, and it arrived to a result, and the result is given here. The final set of parameters is this one, A0, the value for that, for A0 for that parabola. Remember that A0 was the constant term, is a small number, but A1 is even smaller. That's the coefficient of the linear term, and this is the coefficient for the quadratic term. It's also very small, but those are the numbers found by the numerical method. Gnuplot always writes the output of each experiment in a file called fit.log. So if we check that file, we see that we may have experiments dating from previous years. Those are the data that I have used. And as we scroll down and down, we get to the current ones, the ones that you get the date up here. And so this is the last experiment, and all the details are recorded in this fit.log file. And the method used, you see that we have still more and more. So that's great. So that's the content of those files, and that's what the least that needs to be contained within a potential submission. Okay? So what else would you include? I repeat, you would include README files, as many as necessary. Probably only one is necessary, but let me know the details I need to know to run your code. What I want to do is actually to be able to run your code, and I would be doing that maybe not in my machine, because it has its idiosyncrasies, and it's very difficult unless you have a similar computer. The code compiled in another computer wouldn't run here, and so at least it would take me some time to figure out how to replicate the exact environment, and I wouldn't be able to do that if you do not give me enough information, and then I wouldn't be able to grade you. So what happens? One good thing is let's make a tar file for this particular project, and I will show you how to transport this tar file to the computer science server so that you can test it there. Once you are there, you might have to do some tweaking around to make it run in that environment, and then if you can do that, that would be ideal. I can grade you right away because I would be running your code not on my computer but on the computer science server. So let's see, what do I mean by that? So let's say you're ready to submit. This is my final directory, and this is what I want to submit. But before I submit, I need to tune it to pass it to the server, to the computer science server. How do I do that? Well, first we use the SSH and SCP commands from Linux. So what you first need to do is, when you're ready to submit, the first step is always go to the parent directory with cd space ... Okay. Now this is how the parent directory looks like. So of all these directories, I want to make a tar file for the Gale-Shapley directory. So how do I do that? Well, just write tar, then C for create, V for verbose information, want to know everything, and F for file. Then I need to write the name of the target file. I will name my target file with the same name as the directory I want to compress or to tar, and I will just add the .tar extension so that it can be recognized as a tar file. Then this is the directory that's going to be archived. If we want compression, we need to add more parameters, but all this stuff is really very small, so we need no compression at all. And as I hit enter, this is the output I get, the verbose output. It's telling me which different elements within the directories and subdirectories and files within the directories and subdirectories were included in the archive. And if I type ls, now I notice that I have a new file that wasn't there before, which is the Gale-Shapley.tar. It was just created by the tar utility, and it wasn't there before, as you can check in the previous time I run ls. When I display the directories, there's only the Gale-Shapley directory, but not the Gale-Shapley.tar file. And here I have the Gale-Shapley directory and also the Gale-Shapley.tar file. Now that's the file that I'm going to transfer to the computer science server. And how do I do that? Well, first, in my case, I need to find a place for it to land. That means that I need to explore the corresponding space. So see, that's actually the server is student.cs.class.edu files. Just leave it there. So I'm prompted for my password. Then I give my password. Now I'm in. This is the prompt tells me that I am the Gutierrez user from that server. I am at the server called student. That's the one I want. But I just want to go to hard disk that is on the server and not in the particular machine that I landed on. So Now that I am there, I look for, let's say, for one of the, in my case, I may have more than one directory called CSC321 or related like that, related to it. So how about this? So yeah, I have a lot of directories, possible places where I want to put my tar file. Let's see why it's the first one, CSC321. Yeah, and I might see, okay, this is a good place to put my code. This is the place where I would be running it. So I want to take it here. So let's go to directory CSC321. So that, and there you can check with pwd that the path to that directory is just well, home Gutierrez files CSC321. That's my destination path. So it's time to exit the server, computer science server, and back now in my computer right here. But I already know that I want to send, where I want to send this file to. Okay, that was the purpose of the exploration I did before, and it is in this particular directory, files.csc321. So I'm going to do that with the SCP utility, which is a shell copy. I'm going to copy the Gale-Shapley.tar file, and I'm going to copy to the server. So the way you do that is just introduce your username, and again student.cs.plattsburgh.edu : and then the path, which would be files/csc321. And when I do that, I get prompted for my password again. If I make any mistake, I get this report. So now this is a good output, means that the Gale-Shapley file has been transferred in 100%. And this is how much information was moved. So what I want to do is now go to the server and decompress or de-archive my file so I can run it and test it. So let's do that. I would go again with SSH to the server. And then once I am there, I would go to the files CSC321 file directory, and I see I actually have a file named Gale-Shapley.tar in red here. That's a convention that we have in that bash, a configuration in that bash file, in that bash environment. So tar files appear in red. Now we untar it. To do that, we use the same tar utility. It exists also in the server. I am working in the server. I am no longer working in my computer, and I'm working on the student server, the computer science server. And then I'm going to extract. Oh, first I need to add some directives. X for extracting, V for verbose, F for file, then the name of the file I want to untar. And that's success. It means that this output is telling me that the tar file has been de-archived and has been converted into a directory that wasn't there originally, which is this Gale-Shapley directory. And I can just test and go get into Gale-Shapley directory, to the Gale-Shapley directory, and I see all my files. Let's see if my Python file will run. So in that environment, we want to specify Python 2 or 3. I don't know if I'm doing the correct thing. And let's see if, let's try to run this one, and we see that we cannot because it's using NumPy, and NumPy has not been installed. So that would be a problem for anyone using NumPy. So the solution would be, don't use NumPy. NumPy is not really necessary to initialize. You can initialize it with a for loop, write a for loop that will work, and then you will be able to run it here. Don't forget to use Python 2, because if you are following this code any closely, it's written in Python 2.7, and it wouldn't work another way. Let's see what happens with the GS1 GS1 program, which is the object program created for GS1.c, a program written in C, will probably not run here. And as I see, it doesn't run because compile files are very, very dependent on the platform you are compiling. So I need to compile it again. That's one kind of tricking we do. So in this case, I will do the same cc es1.c compile. I want all the warnings, and I want the output file to be named es1, and that's what I get. Those are the warnings. And now let's see if I run GS1 with an input of 1000, then it runs. Okay, and if I run it again, I would get another time. So the code runs here. I needed to do some tweaking in this case. I needed to recompile it. So if you're using any other if your source code is correct, you would be able to compile it in this environment, and that's what you need to do. And for Python, try to adapt to this environment. So you have Python 2 and Python 3, but in neither of those you have the Py27, unless we have unless we activate Anaconda. But I don't want to take you there. Anaconda is a wonderful solution, and I use it in my computer, and I use it also in the computer science server. But it would be a topic for another video or another class. So this is it. I can finally go back to my computer, and now I have something to submit, which is the Gale-Shapley.tar, the one that works. Okay, so you should tweak it, and you may submit from the server, or you may copy back to your computer from the server. How would you copy back from your computer? Let's say let's go back to the server and say I want to copy my tweaked code to my own computer, because remember that I tweaked the code on the server, and then here it is. So the first thing I need to do is to remove that Gale-Shapley.tar file and create another one with the new code, let's say. So then I will see tar cdf and Gale-Shapley tar Gale-Shapley, the directory to archive, and here we have. Now we have a Gale-Shapley tar file that I want to transfer back to my machine. So I exit the server and back in my computer, and now SCP. This is the direction of the file. This is the server's address and then the path to my file. And the name of the file is, I know that it is Gale-Shapley.tar, and a dot to mean I want it here, and I get this. This is what I get. Now, if I type ls, I have a Gale-Shapley tar file. This Gale-Shapley tar file is the archive of the code that has been conformed to work on the Linux environment of the student.cs Plattsburgh server, and that's what I want. So that's what you would submit. Now, from your own machine, just open your Moodle, the Moodle website, and locate the. We will need to jump back to. Let's say this is for the link for the Dropbox is, and I think it is over here. This is it. Then you click on the Dropbox and submit the file that you have already recovered. So that's the description and detailed description of this project.